Alright, and we're back. This is the second video of this practice test. If you clicked on the wrong one, make sure you check out the first one instead. Okay? Alright, so continuing where we left off, alright, we were working backwards through this proof. But now we're stuck, because we need to prove that these triangles are congruent, but we don't know what we're using to do that yet. So let's just keep running backwards through the proof just for fun. And so we have vertical angles. Okay, so what appears to be vertical angles in these triangles? So we have LAF and we have OFM. Oh hey, these two angles. So that's what I would write. Those are my vertical angles. So angle, let's call it AFL, and that's congruent to, now make sure you're naming correctly, right? If I did AFL, I'm going to say MFO to make sure that my triangle's corresponding parts match up. Alright? Be careful about that. So we have that filled in. That's great. Angle 4 has something going on, and I bet it has something to do with this given. So let's look at what that given might be. Okay, so we know that we have length LA is going to be parallel to length, or to segment MO. So if we look here, with parallel sides, what can we do if we have a transversal? Oh, that's right. I think we just did it right here, right? These were parallel, and we had, oh yeah, alternate interior angles, right? Don't forget it. These things keep popping up. So we're going to say alternate interior angles here. Alternate interior angles. And just to double check, we can look at where this is positioned. We have FLA and FOM. Yep, that's true. This one and this one would be alternate interior angles, where LO is the transversal to the parallel lines of MO and LA. Awesome. So we're almost done here. So we've proven this angle and this angle so far. So I'm guessing they're going to prove this side. Well, they could prove any of the sides actually. But I'm guessing they're going for this one because we know that F is the midpoint of AM. Oh, I guessed wrong. We're using AM. So if F is the midpoint of AM, well, what does that mean? The definition of the midpoint? Well, the midpoint's halfway through there. So these are two congruent parts. So we know that AF, oops, hitting wrong buttons. AF is congruent to what? That AF, MF. Oops, why is it? Nah, it always does that. So we have this angle is congruent to this angle is congruent to this angle, and this side is congruent to this side. This looks like it's angle, side to me. If you write it as SAA, that's okay too. I would accept that. That's no problem at all. Alright, so there's number 6 done. Let's move on to number 7. Number 7, same idea. I'm just going to I'm going to fill this out backwards again. If we're looking at this, CPCTC, ooh, that means we're proving this last part, most definitely. So we have angle, oops, angle Q is congruent to, I'm hitting wrong buttons, angle, oh my goodness, angle S. Following that, right, that has to come from having two triangles congruent. Oh look, side, to prove that these triangles are congruent. That's also a hint to the direction of your proof. That means you're proving all the sides are congruent. So we're proving that, I'm gonna start skipping out on notation because of time. QTR is going to be congruent to STR. Make sure you're showing your triangle symbols. Alright, then we see RT is congruent to itself. If it's congruent to itself, that is most definitely the reflexive property. Reflex prop of congruence. So then we look here. This definition of a segment bisector definitely comes from the previous statement where TR is bisecting QS. So if TR bisects QS, QS is getting split into two congruent parts. That would be written as QR is congruent to SR. Thus, working backwards, we must be missing something. Oh yeah, the very first given, where it tells me that QT is congruent to ST. So that's a second given, or the first given, I suppose. And there we go. Set of sides congruent, another set of sides congruent, and another set of sides congruent. That makes SSS. This proof is bing bang bam done. Moving on to number 8. Ooh, CPCTC to prove the last bit. That's definitely going to be EB, segment EB. Make sure you're using your segment, the line above it, is congruent to CB. Okay? Now, proving these triangles congruent, that's a bit different. We got to figure out what's going on. So vertical angles. Do we have a pair of vertical angles here? Yeah, looking at the picture, 1 and 2. So we write angle 1 is congruent to angle 2. Perfect. And then we look here, where is this stuff coming from? Oh yeah, my givens. So given and given. Awesome. So now all that's left is to say, how are these triangles congruent? Well, we have a side, an angle, and an angle. And then side, angle, angle. So this is AAS or SAA. I'll take either way, same difference. So that one was really simple. That's awesome. Now, number 9, we have, okay, so we have our two givens. This time I'm working forwards. So we have our two givens. Why am I working forwards this time? Just because I feel like it. This time, so we have our two givens, so let's write them in there. This is given, given, given. Okay, so those two done. Number 3, isosceles triangle theorem. Okay, now it's important to understand where this is coming from. Isosceles triangles, right, they have two congruent sides, and we know that. We've known that since grade school. But the new thing is that when their sides are congruent, so are the base angles. If we look here, if we look at this as this big triangle of triangle net, NET, we see that angle 1 is congruent to angle 4. Oh my goodness, wait. So two of the angles in the triangle are already congruent. That means their opposite sides will be. This is fantastic. Oops, wrong buttons. Really wrong buttons. Really, really wrong buttons. Sorry, hitting all the wrong stuff today. So we have NE is congruent to TE. Right? We just said that their base angles are the same, so the sides opposite of them are congruent. Sweet. So we now have this angle, this side, and this, or this side, this angle, and this side congruent to this side, this angle, and this side. Oh snap. That just means we can use SSS to prove that our triangles are already congruent. So we can say NAE is congruent to TCE. This is awesome. But now, where are we going with this? You see, now it's saying we're going to use the CPCTC to prove two parts of these outer triangles are congruent. Well, what is it exactly that we need to prove congruent so that way we can use the isosceles triangle theorem? This is where working backwards is beneficial, because I don't know how to move forwards. So I know that I need to prove angle 3 is congruent to angle 2. Alright, angle 3 is congruent to angle 2. How can I do this? Well, if I look at this, if these are congruent, oh, I have another isosceles triangle. That's why they said isosceles triangle theorem. So if I have another isosceles triangle here, that must mean this side is congruent to this side. Oh, that's what my CPCTC is trying to tell me, because since these triangles are congruent here, that means these two lengths are corresponding congruent parts. That's what I need to prove congruent, so that way I can prove that these two are base angles and are congruent to each other. So we can say AE is congruent to CE. And that's number 9. One and done. Now number 10, the dreaded number 10. It's completely blank. So this makes it probably the hardest one on here. So we just need to take everything that we can see bit by bit. Okay? So first let's start with our first given. Okay? So I'm just going to write first given for sake of time. Okay? It's that first sentence right up here, this one. I can't even highlight it because that's written as a picture. Okay? But it's the it's the one with CAV or CAB, triangle CAB is isosceles with vertex angle A. Now, if this is isosceles, what do we know about isosceles triangles? The definition of an isos triangle is what? The sides are congruent. These two sides are congruent. So then, that's what I'm going to write. I'm going to say CA is congruent to BA. Alright, that's cool. What else can I see here? Well, you know what? Let's start with the second given. Let's just get that out of the way. I'm given that AD, segment AD is perp to CB. Alright, what does that mean? Well, it's actually really nice, because that means that if we have perpendicular lines, it forms right angles. That's the definition of perpendicular lines. That, where is it? Angle CDA and angle BDA are right angles. Because of this, now we can say, well, let's see, if we have two triangles and they have a right angle in them, guess what kind of triangles they are? Yep, that's right. By the definition of right triangles, right? To have a right triangle, all you need is one right angle in the triangle. So now we know that both of these triangles, CDA, triangle CDA, I'm not writing the symbol, you should write it, and BDA, both triangles, make sure you write triangles, are right, RT triangles. This is important, right? Because where we're going with this, I'll show you. On the next one, what else do we notice? Well, we can use AD, it's congruent to itself. If we do that, we can say segment AD, make sure you show the segment symbol on top, is congruent to AD by the reflexive property of congruence. I'm just going to type reflex for time. But because of this, we get SSA. Oh, that's bad. But because it's a right triangle, we can now use hypotenuse leg for the first time and say that CDA is congruent to BDA. And now all that leaves is to prove angle B is congruent to angle C by the CPCTC. CPCTC.